let's talk about the review, what we need to learn for the exam. Okay, so let's look at chapter 1, and we're talking about in this thing, the nature of astronomy and science. So make sure you understand that astronomy is an observational science. We can't go do an experiment in space. We just have to look at what the experiments are that are happening out there and study them. So we call it an observational science because we can't set up a controlled environment like a normal experiment on Earth. The nature of science, make sure you understand the scientific method, what constitutes a scientific theory, what's a hypothesis. The most important thing being that in science, any idea that needs that can be affected or studied is scientific. But if you cannot study something, then it's not by definition a scientific idea, because if you can't influence it, can't influence you, and you can't influence it, and you can't study it then, so it can't be part of this process of science. Laws of nature, there are some things that guide everything that happens, cause and effect, and understanding what those things are help us to craft our models and theories to help us create tools to manipulate the universe and use it. Numbers in astronomy, make sure you're just comfortable with scientific notation. So 5 times 10 to the 8th, that thing, 1 times 10 to the 6th, 1 times 10 to the 4, what do those numbers mean? Consequences of light travel time, just make sure you understand the speed of light is constant, it's fixed, and that means that light that we're seeing from far away took a while to get to us. So we're seeing the light today as it was when it left from a distant galaxy. So Alpha Centauri, the closest star to us, the light we're seeing from it is from how it looked 4 years ago, since it's 4 light years away. So make sure you understand that. And then we did a tour of the universe, so make sure you just have a general idea that we are on the planet Earth orbiting the Sun, which is orbiting the Milky Way galaxy, which is part of the local group of galaxies with Andromeda, and we're part of the Virgo cluster in the Laniakea supercluster. And then the broader universe, just make sure you understand that the universe is pretty much evenly speckled with galaxies. There isn't a large area where there's nothing, and there isn't a large area where there's a ton of galaxies. It's pretty much even all the way around. And then the universe of the very small, so just make sure you know that you've got neutrons and protons. Why is a hydrogen atom a hydrogen atom? What is different about it than a helium atom? What about the difference between that and a lithium atom? And then what's the difference between helium 4 and helium 3 and helium 5, or hydrogen 1 or hydrogen 2 or hydrogen 3, which are called deuterium and tritium. Those are the isotopes, so the different neutron numbers. So just be comfortable with that. You won't need a lot of detail on there, but you should be able to explain what's different between hydrogen and helium, and it's 1 proton versus 2 protons, and then hydrogen and deuterium, 1 neutron, no neutrons, 1 neutron, 2 neutrons in the atom. Okay, so just make sure you understand that general construction of the atom. And then a conclusion and a beginning, there's the full calendar year. Understand that we can only see so far back to the edge of the universe. The light that we see is 13.8 billion years old, or about 13.5 billion years old, because the cosmic background radiation is from after what we consider the Big Bang by about 300,000 years or so. You don't have to know that level of detail yet, but you should just understand that it's been about 13.8 billion years to the present time from where we conceivably see the edge of space, basically. And then there's a calendar of when things happened there. You don't have to know on big detail yet. Okay, observing the sky, the birth of astronomy. In this thing, you should just, in this chapter, get out of it just your right ascension declination, your zenith, the celestial sphere, how that works. General things about astrology. I'm not going to quiz you too much on astrology, but just kind of, it's related to where the positions of the constellations are, so just have that sense of it, and make sure you know your sign, because it's important for dating the right person. Okay, and then the birth of modern astronomy. You can learn a little bit about the history there, but I'm not going to quiz you too much on that, but you should be pretty much aware of who the big players are. Copernicus, Kepler, Galileo, and so on, Newton. Those are pretty much the main ones. Tycho Brahe. just because I might use their names in a context, and it would be good if you knew who they were, just to help you understand. Okay, orbits and gravity. Just make sure you know Kepler's laws, that the planets orbit in ellipses, that they sweep out equal areas in equal times. That means a planet will move fastest when it's closest to the host star or body that it's orbiting, and that the further away an object is, the longer it takes to orbit, the longer its orbital period, and that helps us to predict and measure and do all sorts of things. So those are the laws, and then understand that Newton's laws, the object in motion stays in motion unless acted upon by an outside force, that in order to get a change in motion you need to apply a force, and that when you do apply a force, for every action there's an equal and opposite reaction. That explains the force of gravity and how the planets orbit. So Kepler had his laws, and he could predict where the planets would go, and then Newton explained it with one equation how it all worked, and that was the law of gravitation. Orbits in the solar system, so just know the difference between a closed orbit, which is an elliptical orbit, or an open orbit, or an unbound orbit, which is either a parabolic or hyperbolic trajectory. And remember, hyperbolic just means it doesn't have an end, so a parabolic or a hyperbola, they just go off forever in either direction. But an elliptical one, it's closed. Okay, parabolic goes off forever in every direction. Okay, so that's the main difference. Either you can have a star and the planet's orbiting around it, or you could have a comet come in and then leave. You may have heard we've had some interstellar visitors lately, some comets and objects that have a trajectory that is parabolic or hyperbolic. So we watched them travel through our solar system, and they just came to the sun, said hi, and they left. So just be aware of that. And then how do you get an object in orbit? You have to get it going fast enough to reach escape velocity, to get out of gravity, and then if they have enough velocity to be in orbit, then you need to go faster than that to get it out of orbit. So you could put an object in orbit around the moon and then give it an acceleration with a rocket, and then send it off into to deep space, I guess. Okay. Chapter 4 is the Earth, Moon, and the Sky, and the Earth and the Sky and the seasons. So make sure you understand what causes the seasons. That's the tilt of the Earth. Make sure you understand the when and why and how the seasons occur, because you have the equinoxes, and you should understand when those occur and why. So relate that to the ecliptic and the celestial equator and where the sun is. There's two special points. And then the solstices, when in June the longest day, and in winter the shortest day. And then you've got the spring and fall equinoxes, or the vernal and autumnal equinoxes. So make sure you know what causes the seasons, what the equinoxes are, why they happen, and how everything just is caused by the amount of sunlight we receive. Okay? And then keeping time in the calendar, you should just kind of be cursorily aware that we had to eat 10 days or whatever out of the calendar when the Pope Gregory didn't want Easter to get too close to winter, and it started. We had to add the leap year and everything. So just kind of be aware of why that is. Phases of the moon, you should definitely know the phases of the moon. You should definitely know when and why they occur. What is a new moon? What is a first quarter? What is a full moon? What does it mean to be waxing? What does it mean to be waning? If I showed you a picture of a moon, would you be able to identify what phase it was in? You should be able to, okay? And that's really important, because you're going to see the moon all the time, and it's kind of fun to be, hey, first quarter. Hey, it's waxing. Hey, it's whatever. So make sure you understand that. And then ocean, tides, and the moon. Make sure you know what causes the tides, and that there's two kind of types of tides. There's high tides, low tides, and then there's really high tides, which are called spring tides, and kind of high tides, which are called neap tides. So make sure you know when and why those occur and what's different about them, and that's the position of the moon and the sun, which again tells you the phases of the moon too. So all that kind of relates. So make sure you understand that. And then eclipses. Why don't we have lunar eclipses every month? Why don't we have solar eclipses every month? That location of the moon, its orbit has a tilt as well by about 5 degrees off of Earth's orbit, and so that that difference keeps it either out of the path of the sun or out of the shadow of the Earth. And then why is when there's a lunar eclipse can the whole Earth experience it, whereas when there's a solar eclipse only certain parts of the Earth can experience it. So make sure you know all that. Now we get to chapter 5, and again, I don't know if I mentioned it, but definitely right ascension, declination, how that relates to the celestial sphere and that kind of stuff. All right, chapter 5, radiation spectra. The main thing to get out of this chapter is to understand how telescopes work and what we're doing when we look at something with light. And you just remember that light is a signal emitted by an atom, and the energy of the atom generates the energy of the light that you see. So the higher energy light you see, like X-rays or gamma rays, then the higher energy, the more energy the atom had that emitted it, and then down to visible light, microwaves, Wi-Fi, and all that stuff. So that's the full electromagnetic spectrum. And then understand that you can take light, combine it into a single stream, send that off, and it appears as a single color to our eyes, for example. But if you use a prism, you can split it up to the individual colors that went into it. So white light is made out of the rainbow, RGB. Purple light is mostly blue and red, and so on. So that's a magenta, I guess. But if you have violet, then there's literally violet is the color of the light, the energy of the light. So we use spectroscopy in astronomy to figure out what something is made out of by splitting the light it emitted, which tells us the atoms that emitted it. And so by telling us what the atoms were that emitted it, we can figure out what the thing that emitted it is made out of. So that's the importance of spectroscopy. Spectral lines, that's what that is. You use a prism to split a ray of light into its component colors to tell you what atoms emitted what light. Every atom has its own fingerprint. And then the Doppler effect is, okay, so that first part is we can look at the light and use a prism to figure out what it is we're looking at. So we can figure out what something is made out of. The Doppler effect tells us how fast it's moving, either away from us or towards us. So that's an important thing because that is how we figured out that the universe is expanding, is being able to measure the Doppler effect. And so how does the Doppler effect work? It just shifts the wavelengths either closer together or further apart. So it gives the illusion of a slightly higher wavelength and a slightly lower wavelength, or a slightly higher frequency, slightly lower frequency. So what does that mean? It means yellow light, when it hits us, it might look a little bit redder if the source was moving away from us. Or if the source was moving away from us, it would look a little bit bluer, get a blue tint to it. So what that means is I could do something like this, and let's go with this. Hold on a sec. Turn that back on. And okay, here we go. So I could change the temperature of my face. So if I'm moving towards you, okay, then there we go. I'm going to look a little bit bluer than I would normally look. If I'm moving away from you, I'm going to look slightly redder than, there we go, slightly redder, slightly bluer, slightly, okay, I'm going away from you, I'm going towards you. So that's what that means. That's what the Doppler shift is all about. Okay, and then chapter 6 is astronomical instruments. So just make sure that you understand what a telescope is. There's two main types, ones that use lenses and ones that use mirrors. Those are visible light telescopes. Of course, if you're looking at radio waves, it's going to look more like a satellite dish. But make sure you know the difference between a refractor and a reflector telescope. They're general principles of operation. And then there's two types of reflector telescopes, which is Cassegrain and Newtonian. So make sure you know those two differences, just very minimal detail. And then for visible light detectors and instruments, that's where the CCD is. That's how we take pictures of light, is to use, instead of film and instead of using our eye, we use a digital camera called a CCD. And then radio telescopes, so CCDs are in all your iPhones and everything. Radio telescopes, they specifically look at radio waves. So visible light telescopes and radio telescopes are on Earth. They're on the surface of the Earth because visible light and radio waves penetrate the atmosphere and allow us to study them. So if you want to make an observation outside of Earth's atmosphere, if you want to investigate X-rays or gamma rays or ultraviolet or infrared or some other wavelength that the atmosphere absorbs, you have to put the telescope in space. So you have Chandra, you have the Spitzer telescope, Hubble. They're up in space above the atmosphere to get very clear images of those wavelengths of light. And then the future of large telescopes, be aware of the controversy in Hawaii of building the next big telescope on a sacred site and the challenges surrounding that. And then some of the other big telescopes that they're working on in Chile and other places, and understand a little bit of why we're doing that, and then the James Webb Space Telescope. So just be aware of those things. So that's your main thing. You want to be able to just be, what is a constellation? What is an asterism? What are the properties of a constellation, right ascension and declination, pretty much. What is your zenith? What is a meridian? What is your local meridian? What is hydrogen versus helium? How does that work? These are the things that I'll just ask you about. What kind of telescope does this? What kind of telescope does that? If I want to look at planets, which telescope should I buy? If I want to look at galaxies, what's a better telescope? If I want the best bang for my buck overall, a non-cheap telescope, which one might I choose? Um, uh, what phase of the moon is this? What causes the seasons? Um, when is the sun highest in the sky? When is the sun lowest in the sky for the northern hemisphere where we are? Um, what kind of orbit is closed? What kind of orbit could be unbound or open? Um, what causes the tides? If I showed you a picture of the moon and the sun and the earth, I could ask you which tide uh, is this a spring tide or a neap tide, and so on. Okay, and then let's see, spectroscopy. I might ask you about an absorption or emission spectra. I didn't talk about that, but make sure you know about that. Continuous spectrum versus an absorption spectrum versus an emission spectra. And remember, anything that heats up is going to glow a color, and that glow is a continuous spectrum. And then a cold gas could be absorb some of that light, and you'll get an absorption spectrum. Or you could heat up the gas with that, and then the gas will emit light, and that will be an emission spectra. Just depends on those two things. All of that is related to figuring out what something is made out of and how fast it's moving away from us or towards us. And then Wien's law is another thing just to be aware of, the black body, what a black body is. And Wien's law just says that you can figure out what temperature something is just by looking at what color it is. Okay, so just be aware of those things. Okay, that's pretty much everything in the first 6 chapters. If you have any questions, write your comments down below, and I guess I'll see you guys the next time. Okay, bye.